So as stated, today we're going to be talking about maintaining Agile results data in Abaqus. And what that means is making sure that your results databases, in particular ODBs, are small, that they load quickly, and that you're able to take them quickly with you wherever you go. So as stated, I'm the presenter today, Austin Cox. I'm an industry process consultant senior and high-tech industry lead. I've gone to university at Texas A&M back in 2015 is when I graduated, and I was delivering seminars even when I was there to the students. On the agenda today, we're going to be talking about databases, the sources of simulation data, how to keep the data small and agile, and the ODB reducer and builder tool. Databases. What is a database? A database is a usually large collection of data organized especially for rapid search and retrieval. Now, the best thing that I can parallel that to is an Abaqus database is very similar to a library. A library has a collection of books, and all of these have a lot of information inside of them. And whenever you're looking at database size, when you have a very small database, it's very easy to take a small database with you. If you just got a single book, you can take that wherever you like. If you've got a bigger library, if you've got a collection of books, you need some supporting structure. You need kind of a bookshelf. More organization requires sections. If you're in a library, in a large structure, in a large database, you need things like sections, electronic catalogs. You have to consider things like organization, space, speed, and portability. And it's the exact same with Abaqus databases. With a larger database, you have to have more organization. You have more disk space and memory being taken up. You often have a slower speed, and the databases are less portable the larger they get. So if you're trying to store them on disk, you might have to store them to a separate disk if they get too large. Or if you want to transfer them over a network, it may take longer to transfer a larger database than a slightly smaller one. And I've seen that people will try and transfer the databases of sizes in the tens of gigabytes, which is fine over an InfiniBand high-speed interconnect or an HPC. But if you're trying to transfer it from an HPC to your local computer, 10, 20, 30 gigabytes, especially if you're on VPN, can be onerous. So with these large databases, you start losing portability and you start losing speed. You get to have more data in one place, but you have to have that infrastructure in place as well. And libraries need management, they need facilities crew, they need all of these other people to help maintain all of these systems, and they will have people that help you search through the library as well. In a similar manner with historical database formats, Abaqus has gone through a few, such as the FIL, ODB, and SIM. And as we progress, we're able to handle more and more data. We have better infrastructure. However, that takes time to develop. So obviously, whenever you're building something, you build to the technology of the day. And FIL, back when Fortran was king, and ODB C++, and SIM is C++ again. And SIM is able to handle databases that are tens of gigabytes relatively easily. It will still take longer to load more data. However, it has the infrastructure to handle those types of files. For an ODB, something like 20 or 30 gigabytes is quite large. With these large databases, it may take a while to find information. If you've got a single book, it doesn't take long at all to go get it. You just grab it off of your desk. If you've got a collection of books, you have to go find it in your collection of books if you want a particular one. But again, it takes a little bit longer. The entire bookshelf you can't take with you, but you can pick out a single book and take it with. But you have to go searching through that bookshelf. And if you have a lot of books, you have to have a centralized repository. You have to have a centralized place to put these books so that people can access them. It takes space and it has to be put in a centralized location. So it may take a while to find the information you want. So instead of just picking up a book and going and reading it wherever you like, in finding something relatively quickly. If it's a library that the book is in, you have to drive to that library, you have to consult a directory, and you have to walk over to the correct book in the library. And that might be, multiple floors, multiple bookshelves, and it takes a lot longer to find the information. And whenever you want to compute something, for instance, if you want to see how many times Seattle is mentioned in all the geography books in the library, it might take a while. The time is going to depend on how many books there are in that library. If you've got a single book, it's not going to take very long. You just scan the pages. If you've got thousands of books, then you need a different system, and it's going to take longer. This is very similar to Abaqus databases. If you want to do post-processing on a database, it's going to take longer if you have more information. If you want to search for a particular element and ask how close is it to this point in space, if you've only got 10 elements, it's very easy to find out which one's the closest. If you've got 1,000, 10,000, 1,000,000, 10 million, it's going to take longer, and it's going to require different mathematics to find that efficiently. So sources of simulation data. The first thing that we need to understand about all of our simulations is how big of a problem are we dealing with? What's the level of model complexity, i.e. how many books are in that library? As we increase the mesh density and as we increase the number of parts, constraints, contact, we increase the model complexity. And so if we want to do any kind of post-processing, and when we initially load that model into, say, CAE or viewer, it's going to take longer because it has to sort through all of those additional elements. So if you've got the same number of parts but more elements, it's going to, instead of having to sort through 1,000 elements, you might have 10,000, 100,000, a million elements that it has to pull into memory from the disk. And obviously that takes longer. Now, computers are very fast, and we've written the code to be very fast, but regardless of what the infrastructure looks like, if you've got 100 million elements in your model, then it's going to take a long time. We're limited by the speed of the processors, which are typically in the gigahertz range, but you still have a certain number of computations. You have to load the information from disk, and you have to do certain computations in order to at least initially display the elements on screen. We also have to understand how many topics you have in your database. So how many elements determines how big the model is and how long the initial load time is. How many topics you have in your library, i.e. the number of output fields, which is similar to the number of genres in libraries, say fiction or mystery or nonfiction. And that's going to determine the size of the library, the size of your database. And this won't affect the initial load time because we don't load all of these outputs during the initial load because it would just take way too long. But if you're trying to sort through all the different data, you're going to be taking up additional space on the disk. So with additional output requests, if you want to look at the contact opening displacement, the contact pressure, the logarithmic strain, plastic strain, equivalent plastic strain, reaction forces, stresses, displacements, element energies. If you add more and more and more of these, the database obviously becomes larger and larger. And these are able to be output at different places. By default, we have integration point data that's output at integration points. We have nodal data, we have centroidal data, we have element phase data, element phase for something like a pressure, and we have whole element data. So for instance, the status of an element, has it been removed from the simulation or not? And for all of the different outputs, they can potentially be in different positions, but as you add more and more of them, obviously the database size grows. If you want to add religious books to your library, then you need another section of the library. And it's not going to double, but it will grow by another 10, 20, 30, 40%, depending on how many outputs you have already. Another thing that has to be considered is how often. So how many time points, how many volumes of books? If you have a collection of encyclopedias, if it's a 5-volume collection, it's obviously smaller than a 30 volume collection. So if you require a number of output points for your simulation, if you require different points through time for output, then again, fairly obviously, the number of points dictates how much data is getting dumped out to the database. If I request stress only at the very end of my analysis, it's going to take a lot less storage and a lot less space on the disk compared to if I request stress data throughout the analysis of a 50 increment analysis. And then it's quite obvious that my data grows by 50 times in that case. So as we go and solve the simulation, if you're requesting, if you're running a simulation, this is just a play with a distributed load. If you're running simulation, you might have a number of time increments that you solve at, and you don't necessarily need all the information at all those time points. A lot of times you just need the information at the end. Sometimes, however, if you're running a submodel or something similar, then you do actually need intermittent increments during the solve so that you can interpolate between that data for the submodel. So there are times that you can't get around this. And then finally, there's the other consideration of how many runs do you have? So how many times do I need to go solve this simulation? How many different configurations do I have? Essentially, how many times is that output database, that ODB, going to be copied on my disk? If I've got one simulation, fine, everything's going to be just the one simulation. But if I want to change my material types, if I want to go from steel to aluminum to magnesium, or if I want to change my environmental state, if I need to simulate something in a hot state versus a cold state, or under different loading conditions, say another distributed or point load, then I need to have multiple output databases, and any of the single databases is going to be multiplied by the number of runs that I'm going to have to do. So even if you have the same mesh, same everything else, if you're just changing one or two things, however much the original database size was, that information is multiplied by how many runs you're going to do as well. And so that adds up to quite a bit of information. So there's different ways of adding information to your analysis. You can have a larger model, you can have more elements, you can have more time constraints, you have more couplings, you can have more features that get added to a database. You can have more time points that you solve through and that you save data for. You can have different field outputs or history outputs where you're adding information about stress or strain or displacement or connector data or reaction forces. And as you add more and more, you get more information. And then finally, however many runs that you have to do, if you're running this as, if you're making small changes to, the configuration of the model, then, or the environment in which it's running, or you're doing some sort of optimization or something, you have to multiply that entire database by how many times you're running that slightly different simulation. And so as you get more and more information, the databases tend to get a little bit bloated. You can go from having, 100 megabyte database to suddenly finding that you have a 2 gigabyte database, and that might be fine. But also if you're running 50 of them, it's definitely not going to be fine. So that brings us to the question of keeping your data small and agile. If we power through the years, we can see that back in around 1990, I don't have any information before 1999 because I wasn't born then, but around 1990, we had, I think the Cray 2 was out. I think the Cray 3 was just about to come out, if I remember properly. But we have a quote from one of our community papers that due to the size of the FE model, 7,600 elements, a powerful computer was necessary. And that's perfectly acceptable statement. Back in 1990, you had 7,000 elements. That was a lot of information. Through the 1990s, though, we increased processor speed almost every single year. We made significant improvements to our processor speed. And so instead of clocking in at megahertz, our CPUs were suddenly going into tens, hundreds of megahertz, gigahertz. And it was a race to get faster and faster processors. With the 1990s models, we typically had much fewer elements than we do today, obviously. And with something like a truck model, you might model that as a number of components that are tossed in as substructures, and you don't model the entirety of the truck in one simulation because it's too large. And so even though this may only have, in the tens of thousands of elements total, it's too big and it takes too long for the computers at the time. And there are completely the same ideas today. We have problems that are too big. We have things that aren't parallelizable enough, or that we don't have good enough methods to simulate in adequate time. So we might break that apart into a global model and a submodel or a substructure. And it may be a very long time if we ever get away from the concept of breaking models down. And we probably won't get away from the concept of breaking models down into simpler pieces, because that's how you get around not having enough power, is just having the problem broken apart and running everything separately and merging it back together, making assumptions. So through the 1990s, we increase our performance. And around the early 2000s, we start really looking at multi-cores. So instead of a single core CPU, we'd have dual core or quad core. And the early 2000s, we saw this start of parallelization of the code. So instead of running everything monolithically on one CPU, on one processor, and one single core, now we have multiple cores that we're looking at. So now we can split the problem across multiple domains. In 2006, we added our cluster support, so our DMP sparse solver for 16 to 32 cores on your clusters. In 2012, we added GPU acceleration. In 2015, we started having more and more cores. So 2015, we're almost at 100 cores, so on multiple cluster nodes. And we probably even were running on more than 80 cores then. In 2020 and 2021, we've been putting a lot of effort into upgrading our iterative solver for our very large models, tens of millions plus elements. We are running on 1,000 cores. We're running on, say, instead of 4 nodes in a cluster, we're running on 44 nodes of a cluster. And I've seen analyses that run on over 350 million degrees of freedom. 350 million is a little bit more than 7,000, if anybody knows their math, and I hope you do. So with the 1990s, we had small problems, and we're able to do post-processing on that, but database was in the kilobytes range. As we go to the 2000s and beyond, so 2017, we were able to do an entire crash model at once. We don't have to do substructures. We have very detailed analysis. And if you look at the patchwork quilt-looking image, it shows you that this crash model has been broken down over a number of different processors. And so by the time 2017 was there, we have the ability to run these analyses on an entire car without having these submodels and assumptions and everything. We just throw the problem at our CPUs. And by the time 2021 came around, our R&D started having fun, frankly. They said, all right, we can do a single car, we need to test it. Just throw 20 of them in there, we'll make it happen. And so you end up with a little bit of hubris, but that's perfectly fine. Instead of going for a single car, if you want to stress test it, shove a bunch of cars in there. We can test the elements count increasing tenfold. We can test contact increasing tenfold between all of these different assemblies of bodies as well. So as we get to larger and larger models, the amount of information that's stored is obviously going to be much, much larger. So with great power comes great responsibility or great big databases. Back in 2009, we had a community paper on the Boeing Skyhook, And their comment was, in 2000, our servers were 2 dual-core CPU Unix servers. Today, i.e. in 2009, almost 10 years later, we have a Linux cluster with 252 computing cores and more than 960 gigabytes of RAM. So they went up to almost a terabyte of RAM in 2009 on the cluster. Now, I have seen people, and please don't do this if you can help it, but I have seen people run a single job on more than a terabyte of RAM, and that was 3 or 4 years ago at this point. It was great. It was slightly excessive. The person said that the models took too long to run, and I made a couple suggestions on reducing the size of the model and such, but it was, there's a large amount of memory even just to solve the model. So we're getting up to, people might be using a terabyte of RAM to just solve a model, much less put that information on disk. I hope they're not putting a terabyte of information into a single ODB, because I don't even know if that's been attempted before. But so that's 2009, where we had about a terabyte of RAM on the computing clusters. In 2014, there's another aerospace company, Airbus, again, back in a community paper. They had a problem with 70 million degrees of freedom and Lagrange multipliers. They requested displacement at 15 time points, and that ended up with 50 gigabits of data. So just requesting one output at 15 points in time gave them 50 gigabytes of data. So when you start getting to these large models, you really have to consider, how do I minimize the amount of data that goes into my final output database? Because you end up with a very large model. It may take a long time to load. It'll probably take a lot of space on disk, and trying to get that information shoved through the post-processor is going to be difficult. So with that proliferation of data, we have people that are making more refined meshes. They have larger model regions per run. So again, instead of having a truck with substructures, you might have an entire car model all at once. So you make fewer assumptions. There's linearity assumptions and other assumptions that you make whenever you break a problem apart like that. And if you've got the processing power, then you don't necessarily need to do that anymore. So user elements, submodel, substructures, you may not have to do that. But again, that shoves additional information into a single database. People request output more often through time. So instead of having 2 time points, say at halfway and the full way through the simulation, you might request, every 10th of a second for a standard run. So 10 times for the analysis. And that multiplies all of your information by 10 times if you're requesting the field output all at once. You have more output information that you're requesting as well. So stress, displacement, logarithmic plastic, damage, status of contact. You can have more and more and more insights into your analysis, which is great. It's fantastic, but it's not always necessary, and it can keep your databases from performing optimally sometimes. Sometimes you end up with more information than you need. You wanted to go on a road trip and go out to the coast and bring a couple books, and you ended up trying to bring an entire bookshelf. And then if you try and bring an entire bookshelf out to the coast, you got to figure out, how do I get this in my car? Your car wasn't built for that, and it's difficult. You can strap it on the hood or something like that, but you have to have additional things, and it's going to take longer. So those are all the basic things for a single database. And for multiple databases, if you start running the same model across multiple runs, you're going to have more loading and model configurations that you might have. You could be running it as part of an optimization or design of experiments. You could be looking at manufacturing variability, or you could be looking at multi-scale analysis. People like to explore the design space, and in fact, we encourage engineers to explore the design space because it makes them more accurate, it makes them more knowledgeable about the product, and it gives them more options. But again, the cautionary tale is, as you explore the design space and as you add all of these additional runs, you end up with additional data. And so with this additional data, we have to be mindful of the change that we're bringing about. In Seattle and Washington right now, the entire eastern half of the state is closed for the public lands. Nobody's allowed to go on public lands east of the Cascades, the Cascade Mountains right now. And that comes about from multiple different things. One is just overuse of the water, so we don't have as much water anymore to put out fires, but primarily that we haven't done adequate planning or haven't been allowed to do adequate planning to create fire breaks and to create sections of the forest that we cut down in order to keep the fire from catching on to other regions of the state. And what that ends up with is you end up with these people that are, trying to fight all of these massive fires, and you end up with smoke all across the eastern and northwestern US. And some of the best ways to prevent a lot of this is to just do the work up front. And sometimes it's difficult to do the work up front. You may not know exactly what work you need to do all the time, but the more that you can do, the easier it's going to be later. And so the best way to keep your database is small and agile, similarly to how we can keep the forest from burning out here, is to do the work up front. You pay attention to the output requests, do your basic checks. How large will your file be? You can think through that. How can I make any simplifications? If I think I've got 1 million elements, I've got maybe an average of 3 integration points for all of my elements. I've got stress in the 1, 1, 2, 2, 3, 3, 1, 2, 1, 3, 2, 3 direction. So I got 6 components of my stress. If I multiply that by 3, multiply that by 1 million elements, and multiply that by the size of a floating point number, I can get the total size that output request is going to take on disk. And that's a fairly easy calculation to do. And you can make that general calculation for all of the data and get a very quick estimate of about how much data you're requesting. So now it's data time. So I get it, you're busy. No, really, I get it. I was making this presentation quite late yesterday. I get the busy part, but prevention is always the best method. It's best to do your best to only request what's needed. And it takes time to do that. It takes upfront effort in order to try and figure out what information is needed upfront. And the more familiar you are with a specific type of simulation, the easier it is to figure out what to request. But there are specific things that you can do in your input file, in your pre-processing, before you submit the simulation to get a better idea or to reduce the amount of data that is going to be output. One of the first things there is to use the filter parameter. Use the filter keyword. You can use filter in combination with the limit option and extra output frame. And what this does is it triggers output only when a certain threshold is reached. So say that you want an output frame whenever your stress exceeds 700 megapascals. You can use this in order to do that. So that way the output only happens when you hit a specific threshold and you're not requesting a bunch of random output that you may not need. You can also apply different field requests to different categories of data. So that's splitting your field outputs to different groups. So you can have a output group number 1, which is happening at a frequency of, say, 10 times during the analysis. So if you have stress, you may want to output that every 10th of the analysis. And then if you have a second group, you can group your displacement, and your displacement you may need every 100 times during the analysis, but you may not need stress 100 times during the analysis. So it's best to group your output requests. And you may have a group that you only need at the end, so you want to look at the final displacement of everything. So you may, instead of having displacement 100 times, you may only need it 1 time at the very end. Or the same with the contact status or the element energies or something. You can also apply commands on there. You can create keywords that store the integration point quantities at the nodes instead of the integration points. Many purists are quickly going to say that loses a little bit of accuracy. And yes, it loses a little bit of accuracy, but it significantly reduces the amount of data that's getting stored. So instead of storing information at the integration point and having to extrapolate that out to the nodes and then average it at the nodes, you may just store the information at the nodes in the first place so that you don't have to do those extra computations and that you don't have the additional information of having information at all of the integration points, and instead it's only at the nodes, which are typically fewer than integration points. In standard, you can do that by saying position equals averaged at nodes, and in explicit, you can say position equals nodes. And that's great. That's a lot of good information to where you can reduce the amount of data that's getting stored to your database. Now, with nonlinearity, which is our specialty, frankly, sometimes when you're trying to solve a nonlinear analysis, it's like getting dropped off deep in the woods. You can get lost. It's very difficult to see what you're doing sometimes. And even with adequate planning, nonlinear analyses can be unpredictable. You may not know a priori what results are needed or how often, so you may not know exactly how often you need to output the stress or displacement. And this leads to blanket requests of results data. You have nonlinear material behavior that often requires a more refined mesh than a linear material, because you might have plasticity, which is localized to a specific region, and in order to resolve that adequately, you need a refiner mesh. You may request more results data for confirmation and diagnoses that you wouldn't necessarily have to do in a linear analysis. And your workflows may require additional outputs. As mentioned before, if you're running submodeling, you might have many time points that you require during that analysis. So if you've done all of that to where you've done all the work up front, you've minimized the result set that you're going and getting out of this analysis, you say, okay, Austin, I've done the best that I can, but my database is still massive. It's still an oversized beast. Now what? Well, again, let's break it down. No, let's literally break it down. Let's make a new, smaller file focused only on what we need. Now, instead of a library, if the smallest that I can get it is a library, what can I do in that library? If I'm only interested in a certain bookcase in that library, searching through that bookcase is going to be much, much faster than searching through an entire library. So if you've got the results and you know the outcome, you've got the final answer to everything, do you actually need all of this information? Can we get rid of some of the field data? Do we need this history data? I've taken a look at the results. My artificial energy is where it needs to be. It's very small compared to my internal energy. My kinetic energy is low. I've made the assumption that we're quasi-static and my kinetic energy is low compared to all the internal energy. So, you may just want that to have a quick check, but you don't actually need to keep it. You don't need to load it every single time. We have all of these node sets, coordinate systems, all of this other information that I have in here that, again, I may not need. That might have been necessary for the analysis, but I may not need this for my post-processing. And can I focus on a specific region? So it's the same as focusing on a specific bookshelf in the library. Can I focus on a couple of individual components of my overall assembly? Do I need the rest of this stuff, or is it just there so that I had it? And if you have an entire output database and you don't need it, for instance, if I only need one of my lap bands here, then I can potentially break this analysis apart and generate a separate ODB of just the one component. And that brings us to the ODB reducer builder. Now, maybe 3 years ago, I recognized the need that even if you've done your best to minimize the output database size, whenever you run the analysis, there are cases where you're still going to have a lot of data. And there are cases where somebody else might need to look at the post-processing, and they don't need or shouldn't have the entirety of the data that you've solved. So they may not want or need the whole model. They may need, if you've got, say, a wing of an aircraft, they may only need to look at one of the ribs in that wing. Or if you've got, say, a phone, they might only need to look at the camera in that phone because everything else looked fine, but there might have been some damage to the camera when I dropped it. So if I have these results and I've done, a full, say, phone drop, I've looked at the results and I know that I only have to focus on this one component. I don't need the rest of it to look at that one component. I just need the one component. And there wasn't really a way to do that before. So I went and I called it Project Midnight Cowboy because I'm from Texas. I was born and raised in Texas, and I was working on it at midnight in the office sometimes. So it was a project that was born out of the need to minimize the data sets, just to make the models run faster through our Abaqus viewer and through third-party post-processing, and to reduce the size on disk. And there's a number of benefits that you can have whenever you have a smaller database, a database that you're able to break apart. And it used to be called the OEBT, the ODB Extractor and Builder tool. And since it's been incorporated into Abaqus, we've renamed it the ODB Reducer Builder. So we've got a big database. It's too much for us. Let's break it down. Let's create a new ODB from scratch using only the existing ODB and the tool as the input. I don't want to have to solve for a data check. I don't have to do anything else. I have my database. It's got the information. I just want to take a portion of that information out and put it over here. And I want to use that other database separately as its own separate container later. I just want to load that second ODB that's a lot smaller so that it doesn't take forever to load my model. So we have the original analysis that has output, and that output is for a run selected based typically on what you might possibly want or what the solver has to have in order to solve that. And it will dump all that information out to the ODB. But after viewing the results or after solving, you may not need all of that data. You may not have all of the data necessary to keep. Usually it's only a small portion of the initial request that you actually have to do your job. So you might have a result file that's composed of model, field, and history data, and what you actually need is only a portion of that original data. So, wouldn't it be great if we could just create a new result file, a new output database that's a portion of that? And we can take that new one off the HPC and put it on my local laptop and just do some post-processing at home. So if we think about that, what can we improve here by reducing a database? We can improve database speed and database size. If we take a look at the database speed, we can categorize that in a few different ways. One, the initial load. So whenever I click the open button, how long does it take to load that database? We can look at how long it takes the user interface to respond to all of our clicking and everything. We can consider how fast our general computations are if we need to multiply one field by a constant value, or if we need to add fields or do an envelope of fields, or if we have a path that we need to find the closest elements to that path. There's a lot of different operations that are going to be dependent on the size of the database. So frame loading and animations as well. If you've requested more, it's going to take longer to do an animation. So the model complexity, i.e. the number of elements, the number of constraints sets, that goes into the initial load, the interface, the general computations, as well as the animations, so the frame loading, so loading the stress. If you've got more elements, it's going to take longer to do pretty much anything. The number of time points, so if I request at 0.1, 0.2, 0.3 versus just at 1.0, your animations are going to take longer because you have more frames to load. The number of output fields, again, goes back into the frame loading. And the database size is affected by all of these things. The model complexity, number of time points, number of output fields. As you add more data in, the size on disk is going to be larger. And so our goal here is to take the library and reduce it to a bookshelf or reduce it to a single book. We can increase the portability, we can increase the speed. So as an example, if we have a model of an entire aircraft, we may only care about a certain portion of where the side of body meets the wing. So the output tool that we're talking about today, the ORB, is located in a couple different places. If you have Abaqus 2021 or later versions, it's a built-in plugin. You can find it by going to the visualization module and clicking plugins, tools, ODB reducer builder. It's also available on the Smooly community. These versions aren't in lockstep, they're not exactly the same. So there might be slight differences. The Smooly community one is the one that I personally develop and release, and the built-in one is the one that goes through some additional QA and such to be put into the product. So there are a couple different ways to access it. For the usage, and if on the Smooly community, it still has the old name, so you can search on the Smooly community for OEBT. Now, the usage of this tool, you can run it through the user interface, so you can run it using no GUI. In order to run it no GUI, there's documentation on how to do that. But you essentially just say on the command line Abaqus CAE no GUI equals, and the name of the script that's going to be running it. You can use the save or load settings here toward the bottom left in the controls option, and that will apply all of your selections to save that to a file, and you can use that file for other databases that have similar requests. And so you can take that to create an extraction file and use that extraction file in your no GUI if you wanted to. You have all of these master toggles in the features to include on the left here. That is a master switch to turn all of the sets on or off. Same with properties, which is our material sections and profiles, and datums and steps and field outputs and history outputs and such. So if I uncheck sets, it's going to carry no node sets, element sets, or surface sets to the new database. So those are our master toggles there on the left. The right-hand side has a number of different tabs, a tab book that allows fine-grained choosing of features, and we'll talk about that in a minute here. Got about 5 more minutes before I'm going to open up to questions. So I'll go a little bit quickly through the usage here because I think you've got the idea. The first page that we see here is the mesh tab. It defaults to saying whatever's currently on the screen in the viewport, extract that to a new model. So if I have an assembly and it's got 3 components in it, but I only have 1 component on the screen, only that 1 component is going to make it to the new database. And that's based on having the radio button currently displayed selected. You can go into session file. So if you have the same model, same mesh, but a different output database, you can use from session file, typically in the no GUI, to avoid from, say, loading some of the stuff. You have the bounding box, bounding cylinder, bounding sphere, and you can also extract by instances or sets. And the next couple of slides, we'll take a look at this model, the lap joint model. And you'll see we have some history output. We've got a step, steps and frames in there, instances, material sections, et cetera, et cetera. So the next tab in this tab book is the sets tab. And again, I think people that are familiar with Abaqus will find this relatively easy, but there's master toggles on the top again for more specific categories. So you have a toggle for sets back on the left here. And here in the sets tab, you've got toggles for node sets, element sets, surface sets, so you get more specific. And so instead of toggling all of the sets on or off, we can toggle all of the node sets on or off, et cetera. Or if you want, you can choose which specific node sets or element sets or surfaces to carry over to a new database. And so you can click select and then select a few of the sets that you want to carry over. There's some additional capabilities for the no GUI runs with the version on Smooly community. If you're interested, see documentation. It allows you to specify wildcards the same as you can do by the filtering in Abaqus. And you can also specify all except, so the inverse selection of what you choose as well through the Smooly community version running no GUI. We also have the properties tab. So properties is your sections, materials, profiles. This information is in the ODB file by default whenever you run, but you may not want it, so you may not want other people to see it. So we have toggles, again, for each of these checkboxes. And we have radio buttons to either keep all of the data, so I can keep all of the material data, for instance, in the center there, or I can nullify selected, which means get rid of specific data. It'll keep the container for that data, but it'll wipe all of data in that container and it'll default it to the original data. So if I'm looking at a beam profile and I've got a circular profile, the only information in the beam profile is the radius of that beam. And if I have a radius of 5, in the original database, that radius of 5 information is there in the profile. If I choose to nullify that beam profile, the circular beam profile, then what it does is it still says I've got a beam profile, but it says that I have a radius of 1, which is the default value for that radius. So all of the information that you've got in there is defaulted back to the original data instead of maintaining the information that was there for the actual analysis. And so I can do that to specific ones, or I can do that to all of them. So for the aluminum, it will just get rid of all of the extended information, and I'll essentially have an empty container there. Steps and frames. We'd skip datums because datums is very simple. You just choose whether or not you want all the datums or specific or none datums. Step and frame containers, by default, we match whatever your field requests are, or you can choose specific steps and frames that you want in the new database. And this is a blanket thing, so saying that, okay, out of all of my data, I only want these particular frames to make it to the new database. And you'll still have to down select field data for those specific frames in a minute. But this allows you to say, I only care about, say, the last frame in each of the steps. So if I have multiple steps here, I can say, I can select my particular options, or I can say that I only want the last frame of the last step, so the last frame of the analysis, or the last frame of each step. Or I can pick specific ones, and then when I've picked, I click Update Frame Selection, and the preview shows up in the bottom here where it says currently individually selected steps and frames, and that shows you what's going to make it to the new database. And so when we get to the field outputs, they're automatically down selected to mirror whatever the selections are in this tab. So we take a look, we've selected frames 18, 20, and 21. And now when we go to our field outputs tab, we can choose from those 3 individual frames that we selected in the steps and frames tab. So in here, again, I can carry over all the fields, or I can select specific fields. So for those specific fields, I can again select that I only want my strain and my stress in frame 18. I want my strain, my stress, and displacement in 20. And in frame 21, I need my strain, plastic strain, reaction forces, stresses, and displacements. And whenever I select all those, again, you click Update Output Selection, and it shows you the preview in the bottom. Additionally, if you're running a no GUI, you can also specify particular regions for each output selection as well. So I could say that I only want my stress for instance -1 in this particular frame. So we get very fine-grained control over what outputs you want. And then history outputs, currently, there's no fine-grained control. If you're running no GUI, you can pick specific steps for the history output, but nothing additionally inside of that. But please let us know if you want it added. Any demand that you have drives our development. But you can use the master toggle on the left-hand side if you want no history output at all. And in no GUI, you can control based on the step level. So an example of running this is if I have a lap joint model and I only want a particular region, I can just use the display options and drag select a region that I want to carry over to the new database. There's a number of different ways we can do this, but that's one of the easiest ways. Once I select that region, that's whatever is currently displayed. And I can take the ODB extractor and builder, or again, the ODB reducer builder, and I can select some specific sets in there. I can tell it to nullify my titanium. I can choose specific steps and frames and field outputs that I want. And so when you run that analysis, when you run that post-processing, you generate a completely new ODB. You end up, if you don't carry the history output, that gets removed, obviously. And my initial steps and frames, I had 8 frames in step 1 and 2 frames in step 2. And I just kept 1 frame from each of those. So I end up with 1 and 1. I kept specific element sets and node sets, so I reduced the number of element and node sets in there. And my model size has been reduced from 8 megabytes to 750 kilobytes. And it took about 3 seconds to run that post-processing to generate that new database. So obviously it's going to be take a little bit of time to run on a large database, but it absolutely can run on millions of elements. I've tested it on various models. And this will enable you to do a number of different workflows. So we can reduce the database load and computation time for you yourself so that you can work faster with a more responsive program. You can generate a smaller output database so that maybe you can pass it along the network without waiting for 50 minutes, like the image on the right. Or you can store more of them on your disk. You can isolate regions of the models. So if your team does full models and somebody else needs to look at it, but they only are worried about a specific component, then we can break that component off into a new output database. So you don't have to pass them the full model with 10 times the information, which is all irrelevant to them. You can also remove any sort of sensitive data so that you can pass the ODB to a colleague or a company partner or to Simulia support. I've had multiple times where this has helped me diagnose customer issues, and they said, well, we can't pass the model to you. It's got our material information and it's got, proprietary geometry in it. I said, well, if you don't have the material information in there and it's only a subset of the geometry, is that okay? And more often than not, the answer is yes, that's fine. And so a lot of times we can get output databases to diagnose issues that we couldn't have gotten otherwise. So I think we'll skip the demo at the moment since we're getting close to the end of the hour, but we've put in a number of improvements over the years. It takes time to develop this, and just to show you the effort that goes through. We went from running, this is to take an aerospace model, which is about 6 million elements, and copy the model over from one database to the other. The program has gone through a number of improvements over the years, and if you look at the blue line, it took almost an hour to generate the new model, and we put improvement after improvement after improvement in, and it went from blue to orange to gray to yellow to the other blue to black. And so we've reduced from 12 gigabytes of memory to do this operation in about an hour down to 7 gigabytes of memory and about 900 seconds. And we are looking at additional improvements outside of that. So the right-hand side is a change log. That's not code, it's just logging all the different changes that we've done. And this is actually longer than what's in the image because this image was from a year ago. So we put improvement after improvement in, and if there's something that you find, please let us know. If something takes way longer than you would expect, or if there's a feature that you would like to include in here, I built this for you. I built this to make your life easier so that you go home to exercise or be with your children or whatever, so you don't have to wait on Abaqus to finish. With the pandemic, you've probably seen too much of your children, but with Abaqus, you've got large databases. Sometimes it takes a while to do things in if it's too large, and so this is meant to make you more efficient and be able to allow you to not have to wait on the computer and have your own free time. And so with these smaller databases, the only thing that I want to end with here is a quote from Ralph Waldo Emerson, who's one of my favorite poets, is that we ascribe beauty to that which is simple, which has no superfluous parts, which exactly answers its end. And it's my hope that this tool does exactly that.